the equation of one blade is always written in the rotating frame. You understand? Because that is easy to identify what is the motion. Suppose if it is in the non-rotating frame, it is difficult, because after some time blade may be there, then it may be somewhere else. Okay? You write the motion or the degree of freedom beta with reference to a rotating coordinate system, but you get the absolute values. Okay? Are you clear about that? Hub loads are in the fixed frame, because you want to transfer it to the fuselage. Fuselage is not rotating. Please understand, there is one non-rotating frame, there is a rotating frame. In the rotating frame, the blade is moving. So, you are observing the blade motion. That is later when we go, you can't look at a particular blade, but you see a rotor rotating. Suppose you are standing on the ground, you see some rotor is spinning, right? You do not know which blade is coming where, but you see a disc. Okay. Then you are looking at the motion of the disc. We will come to that later, because you are observing the flap motion from a non-rotating frame. You understand? But right now the equation which we have written is observing the motion of one blade as it goes round and round. Okay, is it clear? And it does the same motion, please understand. That is why we wrote beta equals beta naught plus beta 1 c sin psi. So, we wrote this, that this is a, and psi you know, this is psi and this is actually your capital X, right, and this is my, these are hub fixed. This is, you have x 1 and you had y 1, right, and in this x 1 y 1 the blade is moving up and down. So, you are writing the equation of motion in the rotating frame x 1 y 1, because in that frame only how the blade is flapping up and down. How that is beta, that is this quantity, you understand. But this particular, this itself, this is a function of time, right. Time means I can put it non-dimensional time, you agreed. But how I am representing it is in this fashion. Okay. This psi is non-dimensional time only, you follow. So, the blade, what happens is it has a constant flapping, agreed, that is called a coning, plus the value depends on beta, depends on where the location is, but we do not know these quantities, we do not know what they are. That is what that equation is, because that depends on what is the aerodynamic load that acts on the blade, that Fg and R cross, that moment you took it. Okay. That is how you get the flap equation, right. Flap equation is a simple dynamical system equation, which has a, like your mx double dot plus cx dot plus kx equals some f of t. Only thing is m, c, k, they are not constants. M is constant, but c and k are not constants, that is all, they are also varying with time. Okay. So, please understand the difference, and we are looking at steady state response. steady state response is essentially, if you have a fixed harmonic input, that is this, you are giving, see this is my equation of motion, okay, and MF I have written below, okay, that moment due to flap, and of course Lach number is here, input is theta I, okay, theta I is shown as theta naught plus theta 1 c plus theta, okay. This is a non-dimensional time. So, if my input is varying, how my output will vary? Okay. This is a periodic input, because you must have done some at least spring mass damper system. One, if you give an initial condition, actually spring mass damper in electronics, it is a LCR circuit, that is all. If you give an initial condition, how the response will look like? You have under damped, over damped, okay, step response, you must have studied earlier, we will get back to that later. Another one is if you have a harmonic input, that is, if I have this equation 0, I put x of 0 some x naught and x dot of 0 as x dot 0. This is the initial condition I see. Okay. I can analyze how the system will behave. Okay. If this is 0, I give only f dot, that is like a pulse impulse you are giving. Okay. If this is 0, you give this, you are giving initial displacement and leaving it, how the system will respond. The next part is forced vibration. Forced vibration, this is free vibration with damping. Okay. In forced vibration, you would have studied same equation, kx is f of t, but f of t, if you study harmonic motion, you may write f naught some sin omega t or cosine omega t, something like that, where omega is the excitation frequency, input frequency. It has nothing to do with natural frequency. You may have that equal to that. Okay. Now, what we are looking at here is, you convert this into non-dimensional, you may have what, x double dot c over m u x dot plus omega n square x, here you make f over, if you divide by m some, okay. You can do like this, and this you may call it some f naught, some other. This frequency is natural frequency of the system, k root of k over m. This is input frequency. If these two are equal, that is what you call it resonance. Okay. In this problem, what we are analyzing is your input is psi, which is 1 per rev, because the variation is 1 in a revolution, and you see this is also 1, okay, because second derivative this one, damping term is on the right side, that I can transfer it left side. Okay. Please understand, the damping term which is here, this can come back here, but in forward flight you also have additional stiffness term. Okay. That is why we do not write it immediately some frequency, but if it is an hover, no external force, then you say what is the flap frequency. That means mu is 0 and you will have 1. Okay. So, your input frequency is also 1 if it is in hover, but in forward flight you will have all the harmonics, please understand. Because if I put theta I equals theta naught plus theta 1 c theta 1 s sin psi cosine psi, this is getting multiplied by with another sin psi, getting multiplied with sin square. That means, I am having second harmonic, third harmonic, everything comes as an input. Okay. So, my response also will have all the harmonics. So, we are looking at steady state values, and I am not looking at the second, that is sin 2 psi or sin 3 psi, because I restrict my response only up to first harmonic. I am not adding the other terms. I have actually neglected this. You can have sin cos 2 psi, cos 3 psi, everything, you can keep on writing that, okay. But I am neglecting those. Now, if I say I want to get these coefficients, see, this is like a solution of the problem. How do you solve a differential equation with this as the right side and this as the input, theta I as the input? How will you get the beta? Okay. One is you say, okay, I will go and do a numerical integration. Okay. That is the easy way, but you can write closed form solution for this simple problem. Closed form means you can get an expression, closed expression, okay. And that is what I have done it. In the sense, I assume my output is in this form. There are two ways of doing this, I told you. One is the harmonic balance. Harmonic balance means simply substitute everything in that equation, collect the constant terms, collect the cosine psi terms, collect the sin psi terms, you will have equations. That is what harmonic balance is. Each harmonic, collect it separately, write it as one equation, left side equals right side. Okay. Another way is called the operator method, which is simply you integrate. How will you get the coefficients of a Fourier series? You integrate, right, f of t, some integral 0 to 2 pi 1 over 2 pi equal to 0, that is for constant. Then you will multiply by a sin psi, that is for first cosine, you get the second, that is an operator. Same thing you can do for operator method. It really does not matter, both are harmonic balancing only. Okay. One is you doing integration and get the equation, another one is collect all the terms, multiply everything, then write. Okay. When you do that, this is what you get, because I am not doing all those algebra. Okay. So, I am only saying when you do that part, you will get the first, if you make the assumption that beta naught, beta 1 c cosine psi, beta 1 s sin psi, and I do the harmonic balance. When I do harmonic balance, please understand, I am only looking at constant term, cosine psi term, sin psi. If I have on the right hand side some sin 2 psi, sin 3 psi, etc., I am just throwing it out, I do not consider them, I neglect all of them, you understand. I will get these three equations. Okay. And three equations, I know theta 0, theta 1 c, theta 1 s, these are my input, theta twist I know, and what is the forward speed, I know it. Only thing is gamma I know, gamma is Locke number. If you know theta naught, theta 1 c, theta 1 s and the operating condition, I can get from these three equations, because beta naught directly, because it is independent of, there is no coupling. Here beta 1 s depends on beta naught. So, I have to solve this, substitute here, then I can get beta 1 s, okay. And then here is the beta 1 c. Beta 1 c you can directly get it, but it requires lambda. Please understand, you need to know lambda inflow. So, if you are given theta naught, theta 1 c, theta 1 s, mu, lambda, gamma, you can get beta naught, beta 1 c, beta 1 s. That means, if you are specified the operating condition of the rotor, I can get the flap response. Steady state flap response, please understand, steady state means the blade will keep on doing the same thing, okay. And that is what we are getting from this equation. You follow, because why I said is, if you treat flap equation alone as an independent equation without bothering about the helicopter, then if I want the response, I have to know all these quantities. Then you may ask, who gives me my lambda? Okay, lambda should be known before you come to solving these three equations. Please understand, before you solve these three equations to get beta naught, beta 1 s, beta 1 c, you must know what is the lambda, what is the input pitch angle, what is the operating condition, at least that part you must know, because it is not that I do not know that, then what will I do, that part we will come to that later. That is what the trim analysis is. The entire trim analysis is related to iterating between flap motion and then fuselage equilibrium. So, you have to keep going back and forth, that is why it is a complicated analysis, okay. Even the solution procedure is a little complicated. This is a very simplest, that is what I am showing. Now, I will go to a slightly highly restricted condition, that is hover. Same equation, okay. This is just a blade flap dynamics in the steady state response. If I set mu 0, just for, because I am hovering, if I set mu equals 0, this is what I will have from these three equations. I can get what is the beta naught, okay. Beta naught is given by gamma, theta naught over 8, some twist, lambda by 6. That means, to an extent, if you see, this is the lock number, which is aerodynamic force by inertia force. IB will be the rho A C r power 4 over IB. IB is the mass moment of inertia of the blade about the flap. And then of course, collective pitch. This term looks somewhat like CT, okay. Somewhat, it is not exactly, because CT is sigma A by 2, because you know that CT is sigma A over 2 theta naught by 3 minus lambda by 2 in hover, okay. So, it is some crude way of theta by 3, but here it is theta naught by 8, okay. There is a, it is not that same expression, and lambda by 6, okay. But some close thing, it looks similar, theta minus lambda, okay. So, you know that flap coning beta naught is related to what is the rotor loading. If the rotor is loaded more, your coning will be more. If it is less, it will be less, that is all, okay. And then when you come to the cyclic response, that is one S and one C. This is okay. You see, this is somewhat directly related to this angle theta naught. Coning is related to theta naught is related to your loading. Okay. So, you say my beta naught is somewhat related to how much my helicopter is loaded, my rotor is supporting. Okay. If you put more weight, it will go up a little bit. Same operating condition, please understand, it is not that my RPM is changing, fixed RPM. But when you look at this 1C is related to, and because from this equation beta 1 S is related to theta 1 C. That means, when I change my pitch angle, if I take this as my rotor, this is my X, this is my Y, and my psi is, if I change here, pitch angle gets changed here, but I get a because theta 1 C is pitch. If I increase my pitch angle when psi is 0, that means when the blade is here, if I increase my pitch angle, the blade will flap up here, it will go up there, not that it will immediately go up, please understand. Similarly, beta 1 C is related to theta 1 S. Theta 1 S is given here, and the blade will have beta 1 C here, or you can call it beta 1 C. You follow? That means, when I give an input here, if I increase my pitch angle, beta 1 C will become minus. Minus means what? It will go up, because beta 1 C positive means 0 is up, 180 is down. Okay. Whereas, I want if beta, or you may say if my theta 1 S is negative, negative means I am reducing my pitch angle at 90 degree, then what? Beta 1 C is positive, that means the blade will go up. At the back, at the 180 it will come down. So, there is a phase shift of 90 degree between input to the output. Okay. But please note, this 90 degree is only for this simple case of hover plus centrally hinged blade. It will vary the moment I have a different flap model. If I put a spring, it will not be 90 degree, it will change. If I put something else, hinge offset and a spring, it will change. Then how it changes depends on, that is what we will derive, the phase shift between input and output. Now, you know, if the helicopter has to rotor disc is to tilt forward down, you must change the pitch angle when the blade is here, not at the 0. Okay. This is the key important. There is a phase shift of 90. 90 phase shift comes because it is at resonance, because if you have studied little bit more carefully your vibration part of the mx double dot problem, how the phase varies with frequency. all curve, no matter what damping you have, all the phase curves will cross omega over omega and 1, they will cross as 90. That means, when the input frequency is equal to the natural frequency, the phase difference between input and output is 90 degree. Okay. That means, if you give an input now, it effect will be shown after 90 degree, then you convert it to time. Here we know that 90 degree is basically, if I in this disc, if I change my pitch angle here, the response will be here. That I can show it in the lab with the when we rotate the blade, because it is you can see clearly only the stabilizer bar. Okay, you will not be able to see the rotor blade, because rotor blade is rigidly attached. Okay. So, but you can get those from experimentally. So, this is the one of the important results of input to output. Okay. Now, if I change my model, please understand 90 will not be there, 90 will change, 90 will shift, and in forward flight this is in hover condition only, please understand. Now, in forward flight will it be 90? No, it will not be 90, it will be different. But then, because pilot, please understand, now you are slowly, pilot is having a stick in his hand, he will move the stick forward, but what he is doing is only giving a pitch input. Okay. He is not giving flap response, he gives a pitch input. Because of the pitch cyclic variation, the blade flaps, okay, and net result is the rotor disc tilts forward. So, he gets a thrust in that direction. Okay. Now, this is also you can take these two terms on the left side and then you can combine and then try to give a geometrical interpretation. Okay. It is a little interesting geometrical interpretation, I thought I will just show you. That is, all this for only centrally hinged, because when you say centrally hinged, immediately you must know flap frequency is 1 per rev. That means, flap frequency, flap natural frequency is just the rotor RPM itself, nothing else. Okay. Now, let us look at because we defined earlier some different planes. Okay. Suppose you put that this is the shaft and this is the tip path plane, this is my hub plane. Okay. Now, what is this angle? If this is my x direction, this is beta 1 c, right, because this is x and y is down and this is the z direction. Tip path plane is this, but we also defined the no feathering plane. No feathering plane is a plane in which there is no change in the pitch angle. Okay. If that is theta 1s, now look at it, because the plane is like this. Okay. No feathering plane means I am giving a theta 1 s, because in this I am looking at it this way, okay, in this y direction. The pitch angle I give when the blade is at 90 degree, I give a theta 1 s which is positive. you assume that you are giving a positive pitch angle, and then when it comes to 270 you give minus, because sin 270 is negative. So, your hub plane to no feathering plane, it will be, because you are giving a pitch angle like this, there is a theta naught. You have increased one side, you have decreased the other side. That means, in this is 90 degree, you have increased theta naught plus theta 1s, 270 degrees you made it theta naught minus theta 1s. That means, the plane should tilt a little this way, because then you are actually decreasing the, because theta naught is same, theta 1s you have gone up, that means you are trying to reduce the angle. So, your no feathering plane will be, I may draw like this, okay. No feathering plane with this angle, that is theta 1s. Okay. With respect to the hub plane, please understand, all are referred. In the hub, when you look at a blade, pitch angle will be what? Here theta naught, when you go to 90 degree, it is theta naught plus theta 1s, 270 theta naught minus theta 1s. So, you want to make both of them equal, because that means you tilt the plane a little up. As a result, when you are look at that, the angle through which you tilt is theta 1s. That means, you have actually subtracted from here, you have added here, that means my pitch angle is theta naught. In the no feathering plane, the pitch angle is only theta naught. Is it clear? Not clear. See, what happens is, you see this side, this angle is theta naught plus theta 1s, that is at 90. At 270, this is theta naught minus theta 1s. Okay. This is less. I want this angle to increase, means the plane must come down. Here it should be. So, these two lines you join, that is that. Okay. That plane is this plane. So, in the no feathering plane, the pitch angle is constant. In the tip path plane, there is no flapping motion, all tip is going. Now, if you look at the angle between TPP and no feathering plane, that is what? Beta 1c plus theta 1s. This is the angle between tip path plane and no feathering plane, okay, because that is the angle beta 1. This is the hub plane, please understand, this is hub plane, these two are parallel. Port side is theta naught minus theta 1s. Y axis, x axis is here, x is this is x, this is x. See, here aerofoil comes here, okay. I am looking at it, then what will happen? If you look at it, it will be like this. Is it clear? Now, you see the angle between tip path plane and no feathering plane is this. In hover, you look at it, beta 1c plus theta 1s is 0. That means, these two planes must be parallel. That is, this angle should be 0. Okay. This angle should be 0 means what? Both planes must be parallel. So, what, and if you look at the other, this is tip path plane and no feathering plane in longitudinal direction, because you are looking at x and z. If you look at the tip path plane, no feathering plane in the y z, okay, you will get the opposite in the y z. This is x z plane, that is longitudinal plane. Okay. And in the lateral plane, you will have, that is y z plane, TPP and NFP. This will be, because you are giving what, beta 1s. If you look at the yz plane, this is my hub plane, and this is the z axis, and this is my y direction. Okay, this will be beta 1s, this is beta 1s. Okay. And theta 1c will be, because you are looking this way, here you would have added theta naught plus theta 1c, here it is theta naught minus theta 1c. Okay. So, you will tilt the plane like this, because it is more pitch angle. So, you will tilt it like this, which means this will be your NFP with this angle theta 1c. Okay. So, the angle between tip path plane and no feathering plane in this lateral is minus theta 1c. Okay. Now, this is also 0 for hover, but please understand, in forward flight they will not be 0. Forward flight you will have some value sitting there, and that is the function of forward speed. How much is the rotor disk loading? Because please understand, this is, I am again putting it hover. The moment I go to forward flight, these two planes are different, because forward flight I have to solve. If you want, I can show the, I don't know whether I have it. No, it is not here. I have to write it. If the CG is not on the shaft, okay, what will happen is, if the, suppose you have the helicopter, okay, this is the shaft, CG is somewhere here. If you have, then what will happen? So, you have to give cyclic, such that what will happen is, ultimately the resultant, this will come below, so that the helicopter attitude also will change slightly. Shifting in the sense, because this should be right below this, that is all. So, you orient this, suppose orient it means, how do I, because I want this point to be below. Suppose if I rotate it like this, what will happen? I am exaggerating the diagram. Okay. So, the CG has come here. Now, the shaft is like this, maybe I should put it like this. It is a little tough, too much. The shaft is here. I go like this. This is on line. Maybe I Okay. CG is here, tip path plane is horizontal, shaft is tilted here. That means hub plane is like this, okay, which means I have to give a cyclic input depending on the CG location. Okay. That is what happens usually, because depending on the CG location he has to give a cyclic, very little. If it is right on shaft, no problem. Thrust is you take it a hub plane, in the sense it is you will get a horizontal component. That is why in hover, if the CG is right on shaft, if you give a cyclic, helicopter will start moving. Okay, you cannot be in hover and at the same time I do not want the helicopter to move, but I will give a cyclic, no. But if you do clamp it, that means you do not allow the helicopter to move, clamp, what we are doing as an experiment, you give a cyclic, then you will see the tip path plane tilting, okay, doing like this, depending on what input you give. If you give a longitudinal, then it may go, but then that is only for centrally hinged. We can demonstrate that in the experiment. Okay. Now, is this clear? Because the phase shift 90 degree, essentially what the pilot does is, pilot does swash plate plane, which is actually, if there is no other coupling etc., that is the control plane, which is also no feathering plane, if you do not have any other some flap pitch coupling etc. So, he is tilting only this plane, no feathering plane, he tilts, that is all. And because of the blade dynamics, the tip path plane tilts. Okay. He does not tilt the tip path plane, he tilts only the no feathering plane, that is the swash plate. He just tilts lateral at any orientation, and as a result, because you know in hover, in the highly simplified case, they are parallel. So, wherever he tilts, that also goes there. Okay. Now, the question is, you can ask, okay, what is the time lag between his input to that tilt? Okay, you can do that. If there is a time lag, then you will find pilot will give, but then may slowly that will come. That part we will study, because the flap is very quick. Okay. It does within almost 1/4 of a revolution, substantial thing. We will do the time constant and the other thing. Then you will know that is why pilot will not feel that, okay, I give an input, the helicopter rotor takes lot of time to tilt, but that part if you really want to see, we have a small experiment, maybe next class we can bring it, but with the airfoil and without the airfoil. Okay, that I can demonstrate here by showing you just a simple model we have. I will just tilt it, you will see with aerodynamics it will respond very quickly, without that it will come very slowly. So, that seeing is believing. So, next class we will show a video. Video means you have to take the video, but we will demonstrate that motion. Then you will see this is what really happens. Okay. Now, the major part of the flight, the relation between input to flap is clear for a very simplified case. Now, if you complicate the problem, because all this is, that is why usually industry will say what is the input, phase shift 90 degree, but 90 degree is valid only for centrally hinged with flap frequency 1 per rev, that is 1 omega. Suppose if it is not that, which is true, actual helicopters do not have 1, then the phase will change. And is it same in forward flight? Will the phase shift remain constant in forward flight? No, it will not, it will change slightly. Okay. So, now we will go for a slightly more, I would call it an improved model. Okay. Here what I have done is, I put one more spring, because this, once we understand this part, then we can, there are a lot more things even here. I put a, instead of a hinge, I put a root spring which is K beta, which is the flap spring. That will also give a moment. When I move it, it will give. That means, in my equation of motion, I must include this effect, the effect of the root spring. And one more thing I have added in this diagram, that I put a red line and I put a beta sub p, which I call it Precone. That means, my rotor blade in the undeformed position is not horizontal, it is slightly kept at an angle. Okay. When you attach it itself in the manufacturing, in the assembly of the blade, you are giving a coning angle, precone, it is a set geometric angle. Okay. If you put these two, what really happens? Okay. We will just study that part. I will not again derive the entire equation, please understand. That is why I said, once you get one equation, position vector, you take again, rotate it, get the acceleration, get the aerodynamic load. Only load what I have added is a spring. Now, the spring will give a spring moment, which is essentially depends on how much is the deformation. That is, I call it beta is the flap angle. Please understand, beta is measured from horizontal plane, hub plane, but the blade is already kept. That means, how much elastic deformation I give into the spring is beta minus beta precone. Okay. And that much of the moment it will act on the blade. Okay. So, my equation, I will just write that equation, because the flap equation we wrote, inertia is I b into beta double dot, this is the derivative with respect to time, plus omega square, we make that approximation, sin beta is beta, cosine beta is, this is the inertia, and aerodynamic was 0 to r, r f z dr. This was the aerodynamic moment. We said inertia plus external. Now, you have to put the hub moment. This moment is clockwise, whereas the spring, because the aerodynamic lift is this way. Okay. So, if you have that, because the lift is this way, f z, and this is my y axis, y 1, this is x 1, and this is flap, this is r. So, this moment from y axis is a clockwise, that is minus, but when the spring deforms, this will give a spring moment k beta into beta minus beta p, that will be counterclockwise, which is a positive. So, I add k beta into, this is 0, that is all. So, this is my, maybe I should put it a little clear. You will have a spring moment, okay. This is my flap equation, that is all. Okay. Now, what happens? I have to add all of them. and then non-dimensionalize. So, if I do IB, I take it out, I bring this term here, that will be beta double dot plus omega square plus k beta into beta equals, you have k beta into beta p plus integral 0 to r r f z d r. Okay, this is my equation. Sorry, I have to put a IB because k beta over IB, all right. Now, this is like spring by k by m. Okay. So, I am adding additional stiffness to the blade. So, I non-dimensionalize now the entire equation and write it, because this part is straightforward. Only thing is you have to substitute for, I am not writing the entire thing, substitute for Fz, which we know earlier, that is the lift force, lift per unit span, put that value and expand all the terms, multiply and then divide by this dot, convert it into non-dimensional time derivative. So, you will get a omega square. Okay. So, this I can convert it non-dimensional, because this dot is d by dt. So, I put a omega, denominator another omega. So, I will get a omega square. So, when I take out the omega square, I b omega square beta double dot. So, I will have I b omega square into beta double dot plus 1 plus I b omega square into beta. Here you will have again k beta beta p plus your integral f z dr. Okay. Now, I make it completely non-dimensional, then this will become beta double dot plus 1 plus k beta I b omega square beta plus gamma m f. Okay. This will not change. M f is what we wrote earlier. Okay. By adding a spring and a precone, I am getting a constant momentum on the right side. This is the aerodynamic, because gamma is the Locke number, M f is all those theta I, etc. This is my now new natural frequency in flap, which is actually more than 1. Now, I will write it omega bar R f square, rotating flap frequency is 1 plus k beta by I b omega square. Please understand, I have to non-dimensionalize with respect to RPM. This is the omega square. So, this is my, and my non-rotating frequency NRF, non-rotating, NR is non-rotating, because you have a spring, you have IB. If you non-dimensionalize, that will be k beta by IB, and of course, non-dimensionalized with respect to some reference omega. Okay, that is why I put a bar. You do not put 0 value there. Okay. You put whatever. Now, you see my simple equation tells me rotating flap, non-rotating flap is 1 plus. So, this is my rotating flap square is 1 plus omega bar, that is all. Okay. oh sorry, yeah, and this is k beta over I b omega square, that is all. So, if you put a spring, my natural frequency in flap has increased, it has become more than 1. Okay. Now, this is where the industry real problem, how much more than 1 you can keep. Okay. It is a very see, that is where I said we introduce now 2 terms. One is this Locke number, another one is the rotating flap natural frequency. This is natural frequency, please understand. These are the 2 new parameters. Actually, you will find the industry in selecting the rotor system, rotor blade, this is where the major effort goes on. What should be my flap frequency? Okay. It is a real challenging, because this is going to affect my performance, control characteristics, okay, my loads, hub movement, many quantities. Okay. That is why the flap frequency is a very dominant frequency. That is the first flap natural frequency, first natural frequency. We will come to that influence part later. Now, I have modified. Now, I have to get again beta equals beta naught plus beta 1 c plus beta 1 s, all those things. I should solve for beta naught 1 c 1 s. Again I do the harmonic balance. Okay. Maybe I will write that part. This is omega bar R f square beta naught equals minus 1 beta p, this I will send you also, plus gamma. I have done some simplifications here. Okay. Theta twist mu square over 60 minus lambda over 6 plus mu theta 1 s over 6. Okay. This term is identical to, I think, the earlier term. Only thing is I put some 0.8 I added, because that comes because here this is the gamma part is almost same. Okay. Because 60 you add okay, 0.8 location. So, you will get 1 plus mu square you take out. Okay, in this, because you add 1 over 6 minus 1 over 6. Okay. So, that is how you get that mu theta 1 s over 6 minus lambda by 6. But then the next 2 terms is omega bar, this is a little different, minus 1 beta 1 c is gamma 1 over 8 theta 1 c minus beta 1 s into 1 plus half mu square minus mu over 6 beta naught. And then the next one is omega bar R f square minus 1 beta 1 s is gamma 1 over 8 theta 1 s plus beta 1 c into 1 minus half mu square plus mu over 3 theta 0.75 minus mu over 4 lambda plus mu square over 4 theta 1 s. Okay. All right. NFP is mu square minus, yeah. Where is that expression, any mu square theta. Now, this is just a modified form. you have to solve this equation now. If you are looking for, you will see there is a modification in the beta naught, beta 1c, beta 1s because of change in the flap frequency. Okay. Now, you have to solve this equation to get your theta naught, sorry, beta naught, beta 1c, beta 1s. Now, if you take the hover case, because again, because I am coming to simple flight condition, which is the hovering flight condition, because then you said mu is 0. Okay. If you do that, let us look at the only the beta naught part, that is the coning. Beta naught becomes, because your mu will go off, all the mu will go off. Okay. You will have omega bar RF square, because from here you get a very interesting result, divided by omega bar RF square into precone, because this is the precone term is there, plus gamma over omega bar RF square into, you will have theta 0.8 over 8 minus lambda over 6. Okay. Now, there is something called ideal precone. Okay. That is, what should be my, how much I can set. Okay. Because I said that initially blade I attach it at that location. Okay. What angle I would prefer. Okay. If you put it at that angle, the blade will not experience any moment at the root, okay, even though I have a spring, but that is set for only one particular flight condition. This is called ideal precone. Why you want to have a ideal precone? Okay. Because usually all the blades, they are not hinged like this, they have a spring. Spring means it is again an idealization. Okay. Real blade will be different, but it can be made equivalent to this type of blade, because if I give you the flap frequency of a blade, rotating flap frequency, you immediately can find out what should be my k beta, if I know the mass of the blade. If it is centrally hinged, assume that it is centrally hinged, if you know the rotating flap frequency, you know what is my k beta. Okay. So, you can get that this kind of equivalence, you should be able to handle it easily. Now, if you give a precone, what is the effect of that precone? That is, let us look at the, what is the hinge moment that comes. That is, if you have a system, spring, mass and f of t. Okay. What is the force that act here? The force that acts is only kx. Okay. That means the moment that acts at the hub, please understand, this is the flap moment. Flap moment acting at the hub is, I am taking mean value, because beta naught 1c 1s I am not taking, otherwise I have to take k beta, beta minus beta p. Okay. I must take like that. Here I am taking only the mean part of it, 1c 1s I am. So, the mean value, mean hub moment is k beta into beta naught minus beta p. Okay. This is the mean hub moment. Now, I substitute this beta naught here. Okay. If I substitute that, my hub moment, mean hub moment will become, that is k beta, you will have omega bar r f square minus 1 by into beta p 1 minus beta p, then of course, the other term plus gamma over into theta. Okay. And this, sorry, beta, because beta p over this beta p only, right, that is all. So, you subtract, this will become k beta minus okay, plus this value into theta 0.8 by 8 minus lambda over 6. Okay. Because this is minus beta p. Suppose if my beta p is equal to gamma into theta 0.8 over 8 lambda over 6. If okay, that means my moment is 0. Even though I have a spring, my mean hub moment is 0, but I will have some beta 1c and 1s, they will oscillate. That means what I am doing is in my design, because if I get a root moment, my design has to be properly made, because it has to resist the shear force and the bending moment. Okay, like a cantilever beam, if you are taking a beam, you design, okay, what is my root, every section you design for shear and bending moment. If my bending moment is there, I have to design it a little thicker. I can reduce the mean load, okay, only mean load I can reduce it by giving a precone. Now, you know why rotor blades are given slight precone. If it is a only when you have a, if it is a root moment, if it is a pin, there is no, that moment is 0. Centrally hinged, no problem, but the moment you put a spring, which is like, it is like a cantilever first mode. So, you want to give a mean moment, slightly bring it down, rather than otherwise my blade has to be designed little thicker at the root. So, the whole idea of putting a precone is reducing the mean flap moment acting at the hub slightly less. Okay. And this is called this angle, because please understand, you will not eliminate the moment at all flight conditions, because this is valid only for one particular value. If you start flying at another speed, forward, you will have a different flap, then you will get a moment. Okay. Usually the precone they give about 2 degrees, 2 or 2.5, something like that, that is all. Whereas the flap angle may be of the order of around 5 degrees. So, whereas if it is fully tilting to 5, you allow it to tilt only through 2-3 degrees rather than full the 5 degrees, okay, because then the design, that is why all are very important, but it has a effect on damping also, that part we will come later in the stability and other aspects. Right now the precone is given to relieve hub mean moment slightly, otherwise you have to design a bigger hub. So, because the centrifugal force will try to bring it down, the aerodynamic force will try to take it up. If these two moments are equal, it is kept at the same location, that is all. Okay. But if it is slightly up, that is why you can have, if it is fully up, it will try to bring it down. If it is like this, it will take it up. So, that is why usually you do not look at flap deformation, because you, depending on the flight condition, it can come down, it can go up, anything. Okay. Because you can have if the coning is too much, that means your lift is very large, okay, because that is why it is going up. If the coning is very less, means my lift is less. Okay. So, the coning angle changes with your weight condition. That is why all these are just to give some 2 degrees, you relieve the hub moment. It is purely from a design, structural design point of view. Okay. Of course, aeroelastically it will have an effect. That part will come, I hope we will be able to do it, or otherwise we will forget about that aeroelastic effect of beta p on the blade, some stability, etc. Okay. Now, I think I will leave you now, because this is the next part, the phase shift. Okay. How much now, because you have changed the frequency, what will be the change in phase shift? Okay, that part we will do in the next class.